Good morning to all. Today we will discuss energy distribution in black body radiation. In previous sessions, already we discussed introduction to quantum mechanics, definition of black body, construction and the working of Ferris black body. Now today we will the discussion is going on energy spectrum of black body. Before going to that, what is a perfect black body? A perfect black body is a one which absorbs all the heat and radiations irrespective of wavelengths incident on it. When heated to a suitable temperature, it emits total radiation. That's why it's a perfect observer and a perfect radiator. In this context, the energy distribution in the spectrum of black body at different temperatures, the curves will be plotted for the total energy E lambda versus wavelength lambda. The distribution of energy among the different wavelengths of blackbody radiation was studied by Lummer and Pingxing in 1998 experimentally. The curves in the figure shows the variation of intensity for different temperatures of the blackbody. Here, some of the silent features of blackbody radiation spectrum are the general characteristics of energy distribution curves are same for all temperatures. And second one is that the energy is not uniformly distributed at a particular temperature. You consider a single temperature, it is not a uniform distribution is not there in every temperature. From this, we observe that at a particular given temperature, the intensity of radiation increases with a wavelength and reaches a maximum value and then decreases. It's going to decreases. The emission of energy is extremely small for shorter wavelengths and as well as the longer wavelengths. In case of moderate wavelength range, the maximum value of energy is there here for every temperature. From this, with increasing of temperature, the emission of energy is also increases. From this, with the increasing of temperature, the wavelength here we are considered as a lambda maximum, means at what value of the temperature the energy density goes to the maximum is called as a lambda maximum. The lambda wavelength lambda m with corresponding to the maximum intensity is observed from every temperature curve. It is shifted towards the shorter wavelength side. From that, we are writing it is represents Wien's displacement law. When with increasing of the temperature, the lambda maximum value is shifted towards the shorter wavelengths. And another observation is at a given temperature, the area between the curve and the x-axis means it's a wavelength axis. This gives the total energy emitted by the radiation. When this temperature is increases, the area covered under the curve and the lambda axis is also increases. From this, at a particular temperature, the area comes under curve is increases with the temperature is gives the represents the law of Stevens Boltzmann law. It is nothing but E is proportional to T to the power of 4. These silent features are discussed here. This is the at a particular temperature. It is at a particular temperature. The energy is not uniformly distributed along the all the wavelengths. And the second one is nothing but it is at a particular given temperature. The black body emits continuous range of wavelength radiation. As the wavelength is increases, the intensity of radiation is increases. and reaches a maximum value at a particular wavelength. That wavelength is called as lambda m, and then decreases with a further increasing in the wavelength. This means that at a shorter wavelengths and on the longer wavelengths, the lambda energy is very small, and the moderate range of the wavelengths will get the maximum value of the energy is there. And next, at a particular temperature, the wavelength lambda m corresponding to maximum energy density decreases or shifted towards the shorter wavelengths. This is nothing but it is called a Wien's displacement is nothing but a lambda m is proportional to 1 by t, or nothing but also written as lambda m into t is equals to constant. And for all the wavelengths, an increasing temperature causes an increase in the energy emission. Then at a particular given temperature, the area under the curve represents the total energy emitted for the complete spectrum. This area under curve and the lambda axis is directly proportional to fourth power of the absolute temperature of the black body. That is nothing but E is proportional to T power 4 is called represents Stefan's Boltzmann law. From here, we observe that it is a spectrum of a black body. When the temperature is increases, therefore the value of area is also increases. When with increasing the at a particular temperature, at any particular temperature, the wavelength is increases, the energy is also increases and get a reach a maximum value. Then it is going to be decreases when with increasing the lambda. At a particular value of lambda, therefore the energy maximum is there. That value of the lambda is called as a lambda m. Then here we observe that this lambda m into the respective value of the temperature is simply gives the Wien's displacement law is nothing but lambda m into t is equals to constant. In the second case, that every particular temperature, when the area covered under this curve and the lambda axis is gives the total energy radiation, and it is the energy is proportional to t power 4. It gives the Maxwell Boltzmann Stefan's Boltzmann's law. Here we will discuss two laws for the black body radiation. The first one is a Wien's displacement law. Is nothing but we know that it is a state that a product between the wavelength corresponding to the maximum energy of radiation and the absolute temperature of the black body at a constant is simply it is equal is constant. That is nothing but lambda m into t is equals to constant, or lambda m is proportional to 1 by t, or nothing but it is a lambda m is equals to constant by t. Here it is found that the wavelength corresponding to the maximum energy of black body is inversely proportional to the absolute temperature. From that, we draw a curve where we are comparing this Wien's displacement law with Wien's law with the experimental results. When it is the shorter wavelengths, it is coincided with the experimental results. But in case of the longer wavelengths, it is a deviation is observed here from this graph. Means the Wien's law is explained successfully in case of the lower wavelengths, but it is fails at the higher wavelengths. When that is nothing but it's holds good only for the shorter wavelengths, it's not for the longer wavelengths. The second law is also we are discussing here, therefore Rayleigh-Jeans law. It gives the energy distribution of a black body is directly proportional to the absolute temperature T and inversely proportional to the fourth power of the wavelength, where it is nothing but E lambda is proportional to T, E lambda is proportional to 1 by 4. Simply, we can write the E lambda is equals to 8 pi kt by lambda power 4. Here, K is a Boltzmann's constant. When here, this Rayleigh-Jeans law is compared to the experimental results, it holds good for only for the longer wavelengths, and it is failed at the shorter wavelengths. because here we are comparing to the experimental curve, this blue line curve, when this value of curve is coincided with the experimental results, but it is failed in case of the lower wavelength. Therefore, this Rayleigh-Jeans law explain in case of longer wavelengths with respect to the experimental results, but it fails at the shorter wavelengths. Now, here the combination of Wien's law and Rayleigh-Jeans law. The Wien's law is explained successfully at lower wavelengths, failed at the longer wavelengths, but Rayleigh-Jeans law is explained at the longer wavelengths and it failed at a shorter wavelengths compared to the experimental results. These are the different laws in term black body radiation. Now we are going to the failures of Wien's law and Rayleigh-Jeans law was explained by Planck's radiation law, and that it is introduced by Max Planck, is based on the Planck's hypothesis. And it is successfully explains this theory with respect to the experimental results.